Hello, my name is Golubev Kirill and I'm going to talk with you about some derivative and gradients. So at first we will talk some basic material about what is gradient, what is derivative, how do you take it, and what it means. Then we'll talk some advanced stuff about gradient and how it connects to the derivative. So at first I will make a disclaimer because some of you will notice that many things that I will say will not be true in general case. So in this lecture we're assuming that all functions in the world are smooth, and I'm not going to talk a lot about ways to deal with non-smooth one. So that being said, let's begin. If you look at this curve and basically like any curve that's smooth enough, you can notice that if you zoom enough, you will see that it's linear. And one thing that changes is the angle, which I will call alpha here. And it's only based on like a point which we zoom in. So in a long shot, we can define the function that will look like this, for example. Function from f which takes the point, like x0, and give us some function of this angle, like tangents, for example. And this is very interesting to understand how this function behaves and what we can know about it. Okay. Let's investigate the simplest case, and just by your eyes you can see that this angle is the same all the time, and you can define this function that I was talking about as just a constant. For example, as I said before, tangents of this alpha. So how we measure these tangents? So this is pretty much here. And it's worth mentioning that this tangents is the same as k, which are here, and it can be proven by the definition of the tangents, that it is ratio of the two sides of the triangle, this one and this one. So basically here we're just like planting the formula that will work out for us in the more complex case, which will be on the next slide. Okay, here is a more complex case which I was talking about. Here's two lines, one secant line and one tangent line, and basically here is shown that what is happening if it's not linear case. So here you can see that here is one coordinate, here is another coordinate, and these are others. So basically here it's very small, but you can trust me, it's a triangle there that looks something like this. And here is delta y and delta x, and here's our alpha and our function tangents alpha is equal to ratio from delta y to delta x. So what we're doing here is we're making the distance between two axes as small as we can. So basically smaller and smaller and smaller, and miraculously we're making the second line getting closer and closer to the tangent line. So basically we can say that tangent line is the some kind of limit. We will not define it like properly in here, but you can just like imagine how it will work. It's a limit of the second line, but when the points of second line are as close together as they can. So basically you can't distinguish them, but there are still 2 points because you must have 2 to draw a line. So basically this is how tangent line works. Okay, so here's formulas which we know already. Here's which describe this tangent line, and here it is, and here is what are coefficients there. Basically what is said here, here's limit. We will not define it here as I said, but you can see it as this second line from the previous slide, which are like trying to get as close as possible to tangent line by shifting 2 points together. So here is the thing, this value by itself is going to be 0, and this value also will go to 0. So basically here we have like 0 to 0 ratio, which is undefined. And limit theory provides tools to solve these cases and basically to evaluate these limits and ratios of such kind. You can investigate it by yourself, but we don't have time to talk about it here. So you need to know these formulas, but you need to figure out by yourself what they mean. And what you need to remember from it, that you can choose 2 points together enough, close enough, that you can count it as 1 point. That's basically what limit does here. So it's like words, there is a math behind it, but we will not go there. So now we need to define derivative, because we talked a lot about it, but we didn't mention that it's it. So derivative in a point x sub 0 is also it's called f prime from x0 equals to limit as x approaches x sub 0, f from x sub 0 means f from x divided by x sub 0 minus x. So we can define it in any point if curve is smooth enough, and it's smooth enough. So we can make it as some kind of function if we will. We can define it in any point of function, so we can define in all of them. So basically it will be j, which makes a sample from x's and make from this x's a tangents of alpha, which alpha you already know, it's this one. So this is pretty much it, and just we won't call it j, we will call it f prime, and it will be our derivative. Here is why we need derivative. You can read it and understand that you can use it pretty much for every function to understand where decreasing or increasing. It's already cool, but you already been told, I think, that you can find a minimum maximum with derivative. And actually it's tricky part, because if f prime x equals to 0, it's by definition is a steady point, not a minimum or maximum. And here is why. This is f from x that equals to x cubed. And if you'll draw a plot of it, you will notice something interesting. That here is f prime from 0 is 0, but it is not minimum and it's not maximum, because here is function is greater than function in 0, and here is less. So it's not minimum maximum. But what is it? The answer is steady point. It's basically nothing. It's like trick that math or plot plays on you. Okay, here's the thing. I promised you that there will be no theorems, but there are two. The first of them is the sufficiency case for the steady point to become an extremum. So not what extremum is, but basically it's minimum maximum. But for this point, it's important that if it's a steady point and derivative change its side when passing through this point, it's an extremum. Like you can see here with a different color, that here f prime from x is more than 0, and here f prime x is less than 0, because here's function increasing and here is function decreasing. So if you will see here, you will notice that nothing is happening here. In both cases, f prime x here is more than 0. So this brings us to the second theorem, that is about necessity of an extremum. So if some point is extremum and function is smooth enough, that means that in this point of extremum f prime x is 0. So basically, if you will look at from above, you will understand this pattern, that in the first, if f prime x equals 0 and f prime changes its side passing through this point x sub 0, that it means that x sub 0 is an extremum. So the other theorem is like backwards, that if x sub 0 is an extremum, that means that f prime x sub 0 is 0. If function is smooth enough. So here is like, I just can't write it down properly for you not to confuse, because I will use like quanters, and there will be some quanters in next slide, but for now it's like you need to just remember that if f prime x sub 0 is 0 and f prime x changes its side when passing through x sub 0, it's an extremum. And backwards, if x sub 0 is an extremum, that f prime x sub 0 is a 0. So here is some scary math, but do not let it scare you, because it's quite simple. You just need to know how to read it. So the first symbol here, reversed e, can be read as exists. Exists. So and what exists is an area around x sub 0, but which is not contains x sub 0. So it basically like interval around the dot without the dot. So it's okay. This is definitional area or definitional domain. It's basically where your function getting access from. So it's like our big set of access. So how to read it? X sub 0 is a point of local extremum if and only if exists an area around x sub 0 which not contains x sub 0, which itself contained in the definitional area of function f, and for each x in this area, f from this x is less or equal than f from x sub 0. So basically what is told in this definition can be easily shown in the chart, on the plot. For example, you have some curve, and you can see here some minimum and maximums, but how you formalize it? It is local extremum if there is a point x sub 0, which you basically called an extremum, and in his area, which not include itself, are contained only x's which are put in a function f are less or equal than f from x sub 0. So basically they're all less than f from x sub 0. It's basically a local minimum, but in extremum it's a general concept of some interesting point. So it's either minimum or maximum. We're not interested in it, but it's interesting. So basically there are two types of extremums, local and globals, and it's reflected here. So two of them are just about minimum and maximum in local point of view. These two are maximum and minimum in global point of view. So here is the difference. X from the definitional domain and x from this area which not contains x sub 0. So basically in one case you're taking into consideration all points, and in other one you're taking just a tiny bit of them. Okay, here we go. It's again this definition of the derivative. You can brace it, and now I will use it to show you how to use limit and how to make a derivative by definition. I will not explain many things that I will do, but by my actions you will learn something. So I will just at first take a derivative from the linear function. So basically, let's write it down. F from x equals k product x plus b. So f prime x sub 0 equals limit as x approaches x sub 0, k product x plus b minus k product x 0 plus b divided by x minus x sub 0. So at first we're getting rid of b's because of this minus. We can cross them out. Then you can notice that you can bring k from the brackets out, the free and wild. It will look like this. So then you cross out some more stuff, and there it is, the limit from the constant which not depends on x. It's just this constant, so it's k. So f prime by definition of the linear function, it's tangents. So okay, let's do something more interesting, and I will take derivative from the x squared. Why not? F from x equals x squared, then f prime from x equals limit as x approaches x 0, x0 squared minus x squared minus, divided by x sub 0 minus x. So what we can do here, it's actually pretty simple. We will split this x sub 0 squared minus x squared to the product of one sum and one submission. Okay, limit stays untouched. X plus x sub 0, x sub 0 minus x divided by x minus sub 0. So we can definitely cross out something. Crossing out. Then I can tell you it's top secret, but you need to know it. Limit from sum is sum of limits, if limits exist by themselves. So basically I can see that x and x0, x sub 0 as limits are existing by themselves, so I can split them. So that will look like this. And here we go. This is, as you can guess, will be equals x sub 0, and as far as x sub 0 is a constant, this one will also equals x sub 0. So it's two product x sub 0. So this is another one. You can, I think, manage something like this also. And in some time you will find that there is some dependence on this thing and this thing. Actually, two things. Oh, sorry. Yeah, these two things. So there is a general formula that I will show you in a second. They can be proved, but I will not do it because it takes time, but you can practice yourself. Okay, here's some rules. I don't think you need explanation for them, so they're just like plain written. I will just show you that there are good derivative for pretty much all functions that you know. So in on the side of this list, I will make another list of table derivatives, as they usually called. They all are good examples of good task by for getting them by definition, but some of them can be tricky, some of them not. So try how many of them you can get. So okay, first of all, x in power n prime is n product x in the power of n minus 1. So it's pretty simple. Oh, okay, yeah. But the second one is a very cool one. It's an exponential function. If you will make derivative out of it, it will stay the same. Next one is inverse function for the exponenta. It's logarithm. I will use natural one. So its derivative just looks like this. This is actually a good practice task to prove this one. Then there are some less cool. So this one. If you're taking prime of it, it will be cosinus. Cosinus itself prime is minus sinus. Yeah, it's not here. Okay. What else do you need to know? So basically tangents is sinus divided by cosinus, so it's okay to use this rule to solve this one. There are trickier one. They're usually about inverse functions, for example for sinus or cosinus or tangents. Actually there is a rule which are not listed here. Basically it's about inverse functions. I will not list it here also because it's will be complicated to understand, so I will assume you will find out yourself what it is. So this is proven by previous slides. This is inherit its linearity from the limits, because derivatives are limits, and this thing is really interesting to prove because it's not hard, but it's definitely worth a shot. This one is particularly needed for the understanding of the gradient rule, which are applied to the neural nets when they're learning. So make sure you understand this one. So actually there is a trick with this one. You can look at functions as a compositions of some. So basically you can treat 1 divided by x squared as 1 divided by x squared. So you can apply this rule. Also you can treat it like this. You can apply this rule, but it's this one. For example, something more complicated like this, sinus squared in the ratio are only solved by these things. So use them, and you need to use them to understand how many optimizations works which are based on iteration process. Here is an interesting example, x in the power of x. You can apply here some rules from a previous slide, but you can succeed, but it will take you a while, and these functions usually used to show that there are some tricks in getting derivatives. So for instance, it's like nothing you can do about it, but then you can make it a little bit more easy or more complicated. It is fair enough to write this down. Then you can apply a logarithm to both of the parts. And here you can use a chain rule in a very tricky way. From one logarithm you will need to simplify it a little bit. it's fair enough, it can be done. And another one, not. Let it still be this ugly. Then take a derivative from two parts, left and right, and here is, you can apply the product rule, and here is x prime product logarithm of x plus x product logarithm prime of x, and it equals to, applying chain rule, 1 to x in power of x, and then x in the power of x prime. Then you need to look at it and understand that actually this thing we're looking for. What a miracle. Let's solve the equation. We'll pretend that we know everything except the red box. And what a miracle. We made it. Nah, we made it because slide ended. So here it is. X in power of x prime equals to x power of x. We just multiplying both sides of the equation and then simplifying the left side. So x prime is 1. So it's logarithm plus x divided by x. So it's x in power of x divided by logarithm of x plus 1. So here it is, what we needed. This example is dedicated to show you that there are some tricks in derivatives, and you are free to use some nonlinear thoughts about how to take them. Okay, here is some notations to you to not to be confused, and here is probably missing n. So okay, this is Newton's one. They're usually dedicated to physics, so this dot is usually represented, this is derivative by time. So this is actually all you need to know about it. Then this thing, it more interested because you actually can represent, for example, chain rule as a little equation in this notation. So you basically multiplying. It's not actually multiplying because you can't like interact into the symbol itself, but you can imagine that it's multiplication and do something like this. So you can represent f as a function of g, of function of x, and chain rule becomes more beautiful in these notations. So then Lagrange's notations, they're most common, just primes here, indicating that it is a derivative. Also you can see that here is little letters here. There indicates what variables are used to take derivative with respect to. So you can see this thing also. Then there's Euler notations. Euler was in operators, so they are basically the operators of his. They're doing the same stuff, but they can be used to interact with another operators and to produce some funny things. So that's all about notations. Basically, you just need to know they exist. Then we're going to the partial derivatives. It is actually a little bit hard thing to understand, but very easy thing to take if you know derivatives by itself. So basically, all you need to know about partial derivatives that when you're taking one by the variable, you're considering everything else as a constant. So basically, that's written here. So as an example, you can like x plus y prime x will be 1 plus 0. So it will be 1 because it's treated as a constant. Also, something like this, also funny, it will be y will be treated as constant as well. There are some more complicated cases, but to understand how it works, you just need to know that you're using partial derivatives as usual derivatives, but you keep in mind that that y's and z's, which are skipping as constants, are actually variables. And do not forget it, that they can be zeros, they can be negative, they can be like some crappy thing that you not expect from constant. Okay, here we are. We're going to dive into some gradients. And actually, best to explain it, let's imagine the function. Here it is. And let's imagine we want to understand its behavior not only with respect to one variable, but for all of them. We will need to do just thing that is done here. We just can write down everything, every partial derivative from it, and then add up it as a vector. Here it's t for transposing, because vector is a column actually. So for example, it's x plus x squared, like what is their gradient is. So basically you're in the beginning you're dividing by x, considering y is a constant, so it's 1, and then by considering x is a constant, so it's so this is a gradient. And basically it's a full version of the derivative in vector style. So it's a vector. This is a number, and it's called nabla. Here, nabla. And it's it can turn scalars to vector basically. You can imagine some examples by yourself, and they all will be vectors. And here are the notations. But as you can imagine, there are some new things that will add up in with the dimension growth, which are not the same as for single dimensional derivative. So basically, if you will draw it, you will understand that there are some similarities to begin with, and if you consider arrows as the as a pointer where gradient grows, that will basically make you understand how this curve look like. So it's actually helped by a color, but you can also imagine curve without a color, but only with arrows, which is basically gradient. Here is like the color map or temperature map that 0 is a green, and if it become low, it become bluer, and become high, it become redder. And here you can like visualize the gradient, which is like as the arrow makes it through the picture, you can see that it begins to grow. So it's actually like the length of the gradient is like the tangent for the gradient or for the derivative. If it's greater, that means that the function grows faster. So what the downside of the gradient and what makes it tricky? So here's a saddle point, and you can tell why it's called so. So when you're met with a sufficient case for an extremum point, you are obligated to check if derivative of function change sign. But here you can see that there are two directions which it needs to change its sign in. So basically, as more dimensions will add up, you will need to check it more and more and more and more. It's actually quite exhausting. And if you want to check it more like a matrix, because oh no, I won't talk about this. Okay, so basically my point is that the saddle points are the evil points, and if some gradient of function is 0, do not trust it. In the single variable functions, it's easier to check if it's just a steady point, not an extremum, because you can imagine them. But in this case you can't, because can you imagine like 100-dimensional function? Probably no. Nobody can. And this is a problem. You need to check it like analytically. Each time you found a point that you think is an extreme, you need to check the sign of the prime function that they are changing, and you need to check it as many times as twice of amount of variables in this function. So basically it's a tough work. So, but what you can do with that will be on the next lecture about gradient descent algorithm and linear models. So don't be ill. Thanks for watching.